Freeze this frame right here, November 10th, 2025. An amateur astrophotographer captures something moving through the pre-dawn sky, and within hours, thousands of people are staring at the same image, asking the same question: what the hell are we actually looking at? Because this doesn't look like what it's supposed to be. This is 3I Atlas, an interstellar visitor confirmed to be racing through our solar system right now, and the footage that just dropped has astronomers around the world scratching their heads. Some are calling it the most unusual comet ever observed. Others are wondering if calling it a comet is even the right word anymore. Here's what makes this so strange. Comets are supposed to have a visible coma, that fuzzy, glowing cloud of gas and dust that forms when the sun heats them up. It's literally the defining feature of a comet. But in this footage, that signature is missing. The object appears as a bright, compact point of light, sharp, defined, almost geometric. And that's not the only problem. Earlier reports claimed this thing was generating at least 7 distinct jets, streams of ejected material shooting out in multiple directions. 7 active vents should produce a massive diffuse cloud around the object. But here, in frame after frame from multiple independent observers across different continents, it's absent. So either we're all looking at this wrong, or 3I Atlas is doing something that comets aren't supposed to do. And with December 19th approaching, we have one narrow window to figure out which one it is before this thing disappears back into the darkness forever. I'm going to walk you through exactly what's happening here. We're going to break down the footage, compare what the big telescopes are seeing versus what amateurs are capturing, examine the orbital mechanics that make December 19th the critical date, and explore the competing theories about what this visitor actually is. Because right now, the scientific community is split. Some say it's just an unusual natural comet behaving oddly due to extreme conditions. Others point to anomalies in the data that don't fit standard physics. And a small but vocal group, led by Harvard astrophysicist Avi Loeb, is openly questioning whether we should be considering alternatives that most scientists won't even say out loud. This isn't hype. This is documented, peer-reviewed data showing patterns that challenge our understanding of interstellar objects. And the clock is ticking. Let's start with what actually happened on November 10th. Chuck's Astrophotography, operating out of the United States, captures footage of 3I Atlas moving through the sky and shares it via Skywatch Signal. The clip spreads like wildfire across astronomy forums, Reddit threads, Discord servers, packed with backyard astrophotographers who've been tracking this thing for weeks. Within hours, thousands of people are analyzing the same frames. And the immediate reaction from experienced comet observers is confusion, because this object appears as a bright, compact point of light, sharp and defined, almost star-like in its intensity. But this isn't a star. This is 3I Atlas, officially designated C/2025 N1, an interstellar visitor confirmed to be on a hyperbolic trajectory. It came from beyond our solar system, and right now it's racing inward on a path that will bring it closest to Earth on December 19th. Now here's where it gets interesting. Comets, especially active ones approaching the sun, should have a visible coma. That fuzzy glowing envelope of gas and dust forms when solar radiation heats the icy nucleus and causes material to sublimate and escape into space. It's the defining visual signature of a comet, the reason we can see them at all from millions of kilometers away. But in Chuck's footage, that signature is missing, or at least it's not obvious. The object looks naked, bare, like someone stripped away the atmosphere and left only the core exposed. And that's weird, because earlier reports from professional observatories claimed this thing was generating at least 7 distinct jets, streams of ejected material shooting out in multiple directions, some even forming anti-tails that point toward the sun instead of away from it. Think about what that means. 7 jets means 7 active regions on the nucleus, 7 fountains of gas and dust erupting into space. That should produce a massive diffuse cloud around the object. But here, in this amateur frame, it's absent. So the question lands immediately. Is this really a comet, or is the viewing geometry playing tricks on us? Maybe the tail is pointing directly away from Earth, foreshortened into invisibility by perspective. Maybe the coma is there, but too faint to register in a short exposure. Or maybe something else is happening, something that doesn't fit the textbook behavior of cometary bodies. The speed of this object adds another layer of strangeness. 3I Atlas is already confirmed as interstellar. Its orbital eccentricity exceeds 1, meaning it's not bound to the Sun. It came from somewhere else, another star system, a stellar nursery billions of years old. And it's hauling through our neighborhood at velocities that dwarf anything native to our solar system. This is a visitor from the cosmic void, and we have a narrow window to study it before it slingshots back out into the darkness. The buzz is real. Astronomy groups are lighting up. Social media threads are multiplying. Amateur observers from California to New Zealand are pointing their telescopes at the same coordinates, stacking images, comparing notes. And the consensus is forming. This object looks wrong. Not catastrophically wrong, not obviously artificial, just wrong enough to make experienced observers pause and ask questions they're not used to asking. Because here's the thing, we've been observing comets for centuries. We know what they're supposed to look like. Fuzzy, diffuse, surrounded by a glowing halo of sublimated ice. Even faint comets, even distant ones, show that characteristic blur when you stack enough frames. But 3I Atlas, in multiple amateur captures, keeps showing up as a compact, almost geometric point, and that's raising eyebrows. Now let me show you where this gets even stranger. When you compare what the professionals are seeing versus what the amateurs are recording, you get two completely different pictures. Professional observatories have been tracking 3I Atlas since its discovery, and their images tell a different story than the amateur frames. The Virtual Telescope Project, operating remotely controlled instruments in Italy, captured images showing a faint coma and possible tail structure. Gemini Observatory, using advanced spectrograph equipment, detected extended emission around the nucleus. Hubble Space Telescope, the gold standard for high-resolution imaging, recorded structural features, including jets and a diffuse envelope. NASA's public statements confirm this. They note a faint coma and tail for this object. The data is there. The professionals see it. But then you look at Chuck's clip, and you look at dozens of similar frames posted by other amateur astrophotographers across multiple continents, and the object looks completely different. It looks like a star, a bright, compact point with no surrounding fuzz, no visible tail, no obvious envelope, just a sharp dot of light moving against the background stars. And that discrepancy is driving the entire controversy. So what's happening here? Why do the professionals see a comet while the amateurs see a point source? The answer involves technical differences in how the data is collected and processed, but it also opens the door to more unsettling possibilities. Exposure time matters enormously. Professional instruments can integrate light for hundreds of seconds, sometimes stacking multiple long exposures to pull faint signals out of the noise. Amateurs typically work with shorter exposures, maybe 30 seconds at high ISO settings, because longer exposures risk trailing or saturation. When the coma is faint, really faint, it can vanish entirely in a short exposure. The nucleus remains bright enough to register, but the diffuse gas cloud around it drops below the detection threshold, so the amateur sees a point. The professional sees an envelope. Filters also play a role. Many professional observations use narrowband filters that isolate specific emission lines. For example, a filter that blocks most wavelengths except for doubly ionized oxygen emission. That filter can highlight jets and ionized gas structures that would be invisible in broadband visible light. Amateurs mostly shoot with standard filters, which don't discriminate between wavelengths. So the amateur image shows total integrated light, while the professional image shows chemically specific emission. Different filters, different stories. Then there's signal-to-noise and point spread function. Professional telescopes have larger apertures, collecting more photons and producing sharper images with better contrast. That allows faint extended structures to be separated from the background sky noise. Amateur telescopes with smaller apertures have broader point spread functions and lower signal-to-noise. Faint comas get washed out. They merge with the background and disappear.
Viewing geometry adds another complication. If the tail of 3I Atlas is pointing directly away from Earth or directly toward us, it appears foreshortened. Imagine looking at a pencil end-on versus side-on. End-on, you see a dot. Side-on, you see a line. The same principle applies to comet tails. If we're looking down the barrel of the tail, we might not see it at all, even if it's there. And depending on where Earth is in its orbit relative to the object's trajectory, that geometry changes week by week. So the simplest explanation is that the point-like appearance in amateur frames is a data artifact. The coma is there, but it's too faint, too diffuse to register in short exposures with small telescopes under less than ideal sky conditions. The professionals, with their bigger instruments and longer integration times, pick up what the amateurs miss. Mystery solved. But not quite, because some experienced amateur observers are pushing back. They're stacking 40 frames, 60 frames, even hundreds of frames to boost signal to noise. They're shooting from dark sky sites with excellent seeing conditions. They're using processing techniques that should reveal faint extended structures. And they're still getting point sources. No coma, no tail, just a bright nucleus. And that's harder to explain away as simple technical limitation. There's also the question of consistency. If the coma were uniformly faint but present, you'd expect some amateurs to catch it and others to miss it, depending on equipment and conditions. But what we're seeing is a pattern across multiple observers, multiple locations, multiple dates. The amateur community is consistently reporting a compact star-like appearance. That consistency is suspicious. It suggests the absence of a coma isn't just random noise or bad luck. It might be real. And if it's real, if the coma is genuinely missing or severely suppressed in a way that only shows up in certain observational modes, then we have a problem, because comets don't work that way. Comets approaching the sun heat up, ice sublimates, gas escapes, a coma forms. That's basic physics. If 3I Atlas is defying that pattern, we need an explanation that goes beyond exposure times and filters. One possibility is that the object's rotation or orientation creates a situation where the coma is highly asymmetric, concentrated in one direction that happens to be pointed away from Earth during the time window when amateurs are observing. But that requires a very specific geometry, and it doesn't explain why professional observations see the coma while amateurs don't. Another possibility is that the outgassing is episodic. Maybe the object vents material in bursts rather than continuously, and the amateurs are catching it during quiet periods while the professionals are catching it during active phases. But that would require precise timing that seems unlikely given the number of observers involved. Or maybe the coma is there, but so optically thin, so low in density, that it only becomes visible when you use very specific filters or wavelengths. In that case, broadband amateur imaging wouldn't pick it up, but narrowband professional spectroscopy would. That's plausible, but it raises the question of why the coma would be so faint in the first place if the object is generating 7 jets. The side-by-side comparison tells the story visually. Amateur frame, point-like, no obvious coma. Professional frame, faint envelope visible, jets extending outward. Same object, same date, different results. And somewhere in that difference lies the key to understanding what we're actually looking at. But we still have a missing piece. Data that hasn't been released. Data that could settle this question once and for all. And that's where Avi Loeb enters the picture. Loeb doesn't do subtle. As a professor of astrophysics at Harvard and the former chair of the astronomy department, he's built a career on asking uncomfortable questions and pushing boundaries that other scientists prefer to leave alone. And right now, he's asking a very specific question. Where are the HiRISE images of 3I Atlas, and why hasn't NASA released them?
The claim is straightforward. The HiRISE camera, the high-resolution imaging science experiment aboard the Mars Reconnaissance Orbiter, pointed at 3I Atlas on October 2nd and 3rd as the object passed within roughly 30 million kilometers of Mars. That's close. Close enough that HiRISE, with its incredible resolving power, should have captured detailed images, the nucleus, the jets, the surface structure, data that ground-based telescopes simply cannot match because of atmospheric distortion and distance. But as of November 12th, 40 days after those images were supposedly taken, NASA has not made them public. And Loeb is not happy about it. He posted on Medium calling out the delay, tying it to the recent government shutdown and demanding transparency. The implication is clear. Politics shouldn't interfere with science. Data belongs to the public. Release the images. So why does this matter? Why does Loeb care so much about pictures taken from Mars orbit when we already have observations from Earth-based telescopes and Hubble? Because parallax and geometry change everything. Mars was in a completely different position relative to 3I Atlas during the October flyby. The viewing angle was different, the lighting was different. HiRISE might have seen features that are invisible from Earth. Fragmentation, surface texture, jets originating from specific locations on the nucleus, asymmetries that could hint at rotation or internal structure. And resolution matters. HiRISE can resolve details down to a few meters per pixel when imaging Mars surface features. Pointed at an interstellar object 30 million kilometers away, it's not going to achieve that level of detail, but it's still far better than anything Earth-based amateurs can do. If there's something unusual about the shape or structure of 3I Atlas, HiRISE would see it. So why the delay? There are legitimate reasons. Data calibration takes time. Raw images from spacecraft instruments need to be processed, artifacts removed, photometric corrections applied. That can take weeks. There are also proprietary periods where the science team that requested the observation gets exclusive access to the data before it goes public. That's standard practice. It protects the researchers who designed the observation and allows them time to analyze the results and publish their findings before the whole world starts speculating. But 40 days is pushing it, especially for an object as time-sensitive as 3I Atlas. Every day that passes, the object moves farther away, conditions change, follow-up observations become harder. Delaying the release of data that could clarify or complicate the mystery feels like a bottleneck. And in the age of social media, where amateur observers are posting real-time clips and speculation is spreading faster than peer-reviewed publications can keep up, that bottleneck creates frustration. Loeb's frustration is amplified by his history. He's the scientist who argued that Oumuamua, the first confirmed interstellar object detected in 2017, might have been artificial, a light sail, a piece of alien technology. That claim was controversial. Most of the astronomical community rejected it, citing natural explanations involving outgassing and unusual shape. But Loeb stood by his hypothesis, and he's been vocal ever since about the need for scientists to take the possibility of extraterrestrial technology seriously, rather than dismissing it reflexively. So when he sees 3I Atlas behaving oddly, showing up as a compact point in amateur frames, generating complex jets, exhibiting unusual spectroscopic signatures, his radar goes up. And when he sees NASA sitting on data that could shed light on the mystery, he pushes hard. The politics of data in astronomy are messy. Big telescope time is precious. Proposals are competitive. Science teams guard their observations because careers depend on publications, and publications depend on being first. But there's also a principle of transparency, especially when public interest is high and the scientific questions are urgent. The tension between those two imperatives plays out in real time with objects like 3I Atlas. Could the delay be due to something unusual in the images? Something that NASA is reviewing internally before deciding how to release it? That's speculation, pure speculation. But it's the kind of speculation that fills the vacuum when data is withheld. And the longer the delay, the more that speculation grows. There's also the question of funding and bureaucracy. The government shutdown Loeb references in his post disrupted operations across federal agencies, including NASA. Data pipelines slow down, personnel are furloughed, communications break down. It's possible the HiRISE images are stuck in some administrative backlog with no one deliberately suppressing them, just standard bureaucratic friction. But perception matters. When the public sees a high-profile scientist demanding data transparency and NASA remaining silent, it creates a narrative of secrecy, of gatekeeping, of scientists and institutions controlling information that should belong to everyone. And that narrative, fair or not, shapes how people interpret the mystery of 3I Atlas.
While we wait for the missing frames, there's another piece of the puzzle coming into view: the orbital geometry that turns critical on December 19th. That's the date when Earth-based observations reach their optimal configuration. The date when the object is closest, brightest, most accessible to telescopes around the world. The date when we either confirm this is just an unusual comet or start seriously considering alternatives. Orbits tell stories. The path an object takes through space, the speed at which it travels, the angles at which it approaches and departs, all of these encode information about where it came from and what forces are acting on it. 3I Atlas has an orbit that immediately flags it as extraordinary. The eccentricity exceeds 1. That's the threshold. Below 1, you're in an ellipse, bound to the Sun forever, cycling through perihelion and aphelion on a closed loop. Above 1, you're on a hyperbola, an open trajectory that enters the solar system once and leaves forever. 3I Atlas is hyperbolic. It came from interstellar space, and it's going back. Perihelion occurred on October 29, 2025. That's the closest point to the Sun, roughly 1.4 astronomical units, about 210 million kilometers. For reference, Earth orbits at 1 AU. So 3I Atlas passed the Sun at a distance slightly greater than Earth's orbit, close enough to heat up significantly, close enough to trigger outgassing if there are volatiles to outgas. And by all accounts, the object did become active around perihelion. Jets formed, emission spectra showed gas molecules, the professionals detected a coma. But perihelion is not the date that matters most for Earth-based observation. That date is December 19th. On that day, 3I Atlas reaches its closest approach to Earth. Not dangerously close, not even close enough to be visible to the naked eye, but close enough that the geometry is optimal. Roughly 1.8 astronomical units, about 270 million kilometers. That's the distance where large telescopes and serious amateur instruments can achieve their highest signal-to-noise, their sharpest resolution, their best chance to detect subtle features. The geometry matters for another reason. By mid-December, 3I Atlas will be emerging into the pre-dawn sky for observers in the northern hemisphere. It will be high above the horizon before sunrise, away from the glare of the sun, accessible to optical telescopes without the complications of twilight or low-altitude atmospheric distortion. The elongation from the sun, the angular separation, will be favorable. That's the observational sweet spot. Sky and Telescope and BBC Sky at Night magazine publish guides for amateur observers explaining how to find the object, what equipment is needed, what to expect. Magnitude estimates put it around 11.5 at peak, maybe fainter. That means it won't be visible without magnification. You need at least a 6-inch telescope, probably larger, and dark skies. But for those who have the gear and the patience, December 19th represents the best shot. Why does this matter? Because if 3I Atlas is going to reveal something anomalous, something that deviates from standard comet behavior, it's going to happen during this window. The closer it gets to Earth, the more photons reach our detectors, the better our chance of resolving fine structure. If there's fragmentation, we'll see it. If the jets change direction or intensity, we'll see it. If the object exhibits geometric features that don't match natural cometary morphology, we'll see it. And conversely, if December passes and multiple independent observers with high-quality instruments all confirm that 3I Atlas looks and behaves like a normal, if unusual comet, then the mystery deflates. The anomaly gets explained. The speculation fades. We move on. But there's a time limit. After December 19th, the object starts receding. Every day it gets dimmer, fainter, harder to image. By January, it will be magnitude 12 or fainter. By February, magnitude 13. By March, it will be beyond the reach of most amateur equipment and will require dedicated professional telescope time to observe it all. And professional telescope time is rationed, competitive. There's no guarantee anyone will bother tracking it once the initial excitement fades. So this is our shot. December is the window. And within that window, December 19th is the bullseye. There's also the question of what we're looking for. If the object fragments, if it breaks apart into multiple pieces, that's detectable. Fragmentation is common in comets under thermal stress, especially interstellar comets that might be structurally weak from billions of years of cosmic ray bombardment. If we see fragments, that supports the natural explanation. It's a rubble pile held together loosely, coming apart under solar heating. If the jets change configuration, if they suddenly shift direction or intensity in a way that doesn't correlate with rotation or solar heating, that's interesting. Natural jets can be episodic. They can rotate with the nucleus, but they follow predictable patterns. If 3I Atlas shows jets that violate those patterns, we need a better model. And if the object exhibits geometric regularity, if the shape or the surface features or the emission pattern show symmetry that's hard to explain with natural processes, that's where things get speculative. Nature loves asymmetry. Comets are lumpy, irregular, chaotic. Perfect symmetry, or even approximate symmetry, is a red flag. Not proof of anything artificial, but a flag. The limitations are real. Even at 1.8 AU, we're still talking about an object that's maybe a few kilometers across, possibly smaller, observed from 270 million kilometers away. The best ground-based telescopes can resolve features down to a few hundred meters under ideal conditions. That's not enough to see surface details, not enough to distinguish between a natural nucleus and a hypothetical artificial structure, unless that structure has large-scale features. But spectroscopy helps. We can measure the composition of the outgassing material. We can look for anomalies in the gas ratios, unusual molecules, emission lines that don't fit standard cometary chemistry. We can track the non-gravitational acceleration, the subtle changes in trajectory caused by outgassing thrust, and see if it matches the expected pattern. All of that data converges in December. And the result, whatever it is, will shape how we think about interstellar objects for years to come. So, with the date locked, with the observational window defined, we need to map the intellectual battlefield. What might this object actually be? What are the competing hypotheses, and what evidence would support or falsify each one? Hypothesis 1 is the simplest. 3I Atlas is an unusual natural comet. It formed in another star system, got ejected into interstellar space, spent millions or billions of years drifting through the void, and now it's passing through our solar system for the first and only time. The jets, the high carbon dioxide to water ratio, the unusual polarity signature, the compact appearance in amateur frames, all of this is explainable within the boundaries of known physics. Extreme viewing geometry makes the coma hard to see. The carbon dioxide dominance reflects formation conditions in a colder, more carbon-rich environment than our solar system. The jets are just active vents on a rotating nucleus. Nothing here violates comet physics. It's just on the edge of the distribution, a statistical outlier, but not an impossibility. What would support this hypothesis? If further high-resolution imaging from Hubble or ground-based adaptive optics systems shows a natural irregular nucleus. If the spectroscopy remains consistent with known cometary volatiles, like water, carbon monoxide, carbon dioxide, ammonia, methane, even if the ratios are unusual. If the non-gravitational acceleration matches the expected thrust from measured outgassing rates. If the object fragments under thermal stress, proving it's a fragile aggregate held together by weak forces, all of that supports the natural comet hypothesis.
What would falsify it? If spectroscopy detects molecules that don't form naturally in space. If the jets show configurations that can't be explained by rotation and solar heating. If the object exhibits geometric regularity or symmetry in its shape or emission patterns. If the non-gravitational acceleration doesn't match the outgassing thrust. Any of those would push us toward alternatives. Hypothesis 2 narrows the natural explanation. 3I Atlas is a fragile, fragmenting rubble pile. It's not a single solid nucleus, but a collection of smaller pieces held together by weak gravity and possibly frozen volatiles acting as glue. This would explain the high outgassing rates, the complex jet morphology with 7 or more distinct streams, and the potential for rapid changes in appearance. Rubble piles can fragment suddenly under thermal stress, ejecting pieces that themselves become mini comets. That could create the illusion of multiple objects or complex structure.
Supporting evidence would include direct observation of fragmentation, seeing pieces separate from the main body. Rapid changes in brightness or jet configuration as chunks break off. Variability in the light curve that suggests an irregular tumbling shape. Spectroscopic evidence of exposed subsurface material as layers peel away. Falsifying evidence would be structural stability. If the object remains intact, if the light curve is smooth, if the jets remain stable over weeks, then it's probably not a rubble pile on the verge of breakup. It's something more coherent. Hypothesis 3 is where things get controversial. 3I Atlas is a technological or engineered object. This is the Loeb hypothesis, the idea that we're looking at something artificial. Either a spacecraft, a probe, or a piece of defunct technology from another civilization. The missing coma fits because there's no outgassing. The compact appearance fits because the object is solid metal or ceramic, not ice. The jets fit because they're not jets, but exhaust plumes or vented gas from internal systems. The high carbon dioxide ratio fits because it's not sublimated ice but chemical propellant. This hypothesis makes extraordinary claims, and extraordinary claims require extraordinary evidence. What would support it? Detection of industrial materials, metals or alloys that don't form in space. Geometric regularity in the shape, cylinders, spheres, faceted structures. Jets that pulse on a regular schedule, inconsistent with natural outgassing. Non-gravitational acceleration that's too strong or too directional to be explained by comet physics. Radio emissions, artificial signals, modulation patterns. Any of those would elevate this hypothesis from speculation to serious consideration. What would falsify it? Spectroscopic confirmation of natural cometary volatiles. Fragmentation proving it's made of ice and rock. Jet behavior that matches rotation and solar heating. Surface textures consistent with natural aggregates. Basically, if it quacks like a comet, swims like a comet, and tastes like a comet, it's probably a comet. Hypothesis 4 is the skeptic's favorite. The anomaly is an observational or processing artifact. There is no mystery. The missing coma in amateur frames is due to short exposures, small apertures, poor seeing conditions, or inadequate stacking. The professionals see a coma because they have better instruments and more time. The unusual jets are real but explained by standard outgassing physics. The high carbon dioxide ratio is unusual but within the range of natural cometary chemistry. The whole thing is a case of pattern seeking, confirmation bias, and hype amplified by social media. Supporting evidence would be additional high-quality amateur observations that do show a coma, proving it was always there but just faint. Professional spectroscopy showing nothing anomalous. Models that reproduce all the observed features using standard comet physics. Basically, the anomaly vanishes under closer scrutiny. Falsifying evidence would be consistent reports from multiple independent observers with high-quality equipment, all confirming the missing coma. Professional observations that also show anomalies. Data that can't be explained by artifacts. So we have 4 frameworks: natural comet, rubble pile, technological object, observational artifact. The tests are clear. HiRISE images, if released, will help by providing independent high-resolution data. Spectral composition studies will distinguish between natural and artificial chemistry. Non-gravitational acceleration models will reveal whether the thrust matches outgassing or not. Fragmentation monitoring will test structural stability. Polarimetric studies will probe surface texture. Recent research adds nuance. A study of galactic cosmic ray processing found that interstellar comets exposed to high-energy radiation over millions of years can develop extremely high carbon dioxide to water ratios, as carbon monoxide gets converted to carbon dioxide. That supports the natural explanation for the unusual chemistry. It means 3I Atlas doesn't need to be artificial to have a weird gas ratio. It just needs to be old and heavily irradiated. But that same study doesn't explain the missing coma or the compact appearance. So we're left with a mixed picture. Some anomalies explained, others still hanging. The intellectual battlefield is crowded. Scientists, enthusiasts, skeptics, all of them are watching the same sky, looking at the same object, seeing different things. And December will force a reckoning. Now let's talk about those 7 jets. Because understanding jet morphology and dynamics is critical to figuring out whether we're looking at one nucleus with multiple vents or multiple fragments each generating their own emission. Jets are windows into a comet's interior. When the sun heats a comet's nucleus, subsurface ices warm up and sublimate, turning directly from solid to gas without passing through a liquid phase. That gas, along with entrained dust particles, erupt through cracks and vents in the surface, creating narrow streams that shoot outward at hundreds of meters per second. The direction of each jet depends on the location and orientation of the vent. The intensity depends on how much material is escaping. And the morphology, the overall pattern of jets, tells you about the nucleus's shape, rotation, and thermal properties. 3I Atlas is reportedly generating at least 7 distinct jets. That claim comes from earlier reports describing multiple emission streams around the object. Some forming what observers call anti-tails, jets that point toward the sun instead of away. 7 jets is a lot. It suggests a highly active nucleus with multiple vents scattered across the surface. But it also raises questions. How do we know it's one nucleus generating 7 jets and not multiple fragments each generating their own emission? The geometry of jet emission is governed by simple physics. If the nucleus is rotating, which all comets do, the jets rotate with it. Observers see the jets sweep across the field of view like searchlights on a spinning stage. If the rotation period is short, the jets blur together into a diffuse fan. If the rotation period is long, the jets appear as discrete structures that change position slowly over hours or days.
For 3I Atlas, the reported jets are distinct and appear in multiple directions. Some point away from the sun, which is expected. Solar radiation heats the day side of the nucleus, and the warmest regions vent the most gas. But other jets appear to point sunward, forming anti-tails. Anti-tails are not actually jets pointing toward the sun. They're optical illusions caused by viewing geometry. When you look at a comet's tail edge-on, the dust particles along the outer edge of the tail can appear to project in front of the nucleus, creating the illusion of a tail pointing the wrong way. It's a perspective effect. But if the anti-tail interpretation is wrong, if these are actual jets pointing sunward, then we have a problem. Natural jets don't do that. Solar heating creates pressure gradients that push gas outward, away from the heat source. A jet pointing toward the sun would require some other force. Maybe the nucleus is tumbling chaotically, and vents on the night side are momentarily pointed sunward. Maybe there's an internal heat source warming regions that aren't directly illuminated. Or maybe it's not a natural jet at all. The possibility of fragmentation adds complexity. If 3I Atlas is not a single solid body, but a cluster of smaller pieces, each fragment could generate its own jets. The overall pattern would look like 7 or more jets around a single nucleus. But in reality, you'd have multiple nuclei, each with 1 or 2 jets. That would explain the complexity. It would also explain why some observers report changes in the jet configuration over time. Fragments drift apart, their relative position shift, and the overall pattern evolves. Fragmentation is common in comets. Thermal stress, tidal forces, and rotational spin-up can break a weakly bound nucleus into pieces. Comet Shoemaker-Levy 9 famously fragmented into more than 20 pieces before impacting Jupiter in 1994. Comet Schwarzmann-Wachsmann 3 split into multiple fragments during its 2006 apparition. If 3I Atlas is a rubble pile, a loose aggregate of ice and rock held together by weak gravity, then fragmentation is not just possible, but likely. But distinguishing between a single nucleus with multiple jets and multiple fragments with individual jets requires high-resolution imaging. You need to resolve the nucleus itself, see its shape, count the emission sources. Ground-based telescopes struggle with this. Even Hubble, with its excellent resolution, can only barely resolve the nucleus of 3I Atlas at its current distance, so we're stuck making inferences from the jet pattern. One approach is to model the dynamics. If you assume a single rotating nucleus and calculate where vents would need to be located to produce the observed jet directions, you can test whether the model is self-consistent. If the model works, the single nucleus hypothesis holds.
If the model requires vents in physically impossible locations or orientations that violate rotation mechanics, then fragmentation becomes more likely. Another approach is to track changes over time. If the jet pattern remains stable, that suggests a single rotating body with fixed vents. If the pattern changes rapidly or unpredictably, that suggests fragmentation or some other transient process. Ejection velocities also matter. Typical cometary jets have velocities around 500 meters per second to 1 kilometers per second, depending on the volatiles involved and the temperature. Carbon dioxide jets can be faster because CO2 has a lower molecular weight than water and sublimates at lower temperatures. If 3I Atlas shows jets with velocities outside this range, either much faster or much slower, that tells you something is unusual about the outgassing mechanism or the material being ejected. There's also the question of jet stability. Natural jets can be episodic. They turn on when solar radiation warms a particular region and turn off when that region rotates into shadow or when the vent gets clogged with dust. But the timescales are predictable. A jet tied to rotation should show periodic behavior, matching the spin period. A jet that appears and disappears randomly suggests something more chaotic, possibly fragmentation or structural failure. And here's where the speculation gets interesting. If the jet pattern shows regularity, if the jets are spaced at precise angles or fire in synchronized sequences, that's hard to explain with natural processes. Natural vents form where structural weaknesses exist in the nucleus. They're randomly distributed, or at least distributed according to thermal and structural factors that don't produce geometric regularity. Precise spacing or synchronization would be a flag. Not proof of anything artificial, but a flag that demands deeper investigation. The data we need is clear. High-resolution imaging to resolve the nucleus and count the emission sources, time series spectrometry to track changes in jet configuration, spectroscopy to measure ejection velocities and composition, and patience, lots of patience. Because this data takes time to collect and analyze. But jets are only part of the story. How fast the object is accelerating or decelerating gives even deeper clues. Non-gravitational forces, the subtle pushes from outgassing, reveal whether 3I Atlas is behaving like a normal comet or something else entirely. Gravity is clean, predictable. You can calculate the trajectory of any object in the solar system to arbitrary precision using Newton's laws and general relativity corrections. But comets cheat. They don't follow pure gravitational orbits because they're constantly losing mass, and that mass loss creates thrust. It's the rocket equation in reverse. Instead of burning fuel to accelerate, the comet sublimates ice to produce gas that jets outward. And by Newton's third law, the nucleus recoil. That recoil, small as it is, accumulates over weeks and months, and it changes the orbit. Astronomers call these non-gravitational accelerations, and they're a standard feature of cometary dynamics. You measure the comet's position at multiple times, calculate where it should be based on gravity alone, and see how far off the actual position is. That difference tells you the magnitude and direction of the non-gravitational force. For most comets, it's small, a few centimeters per second squared, enough to shift the orbit by thousands of kilometers over a close solar approach, but not enough to violate any laws of physics. 3I Atlas is producing non-gravitational accelerations, and the numbers are interesting. Swift ultraviolet data indicates a water mass loss rate of roughly 40 kilograms per second at a heliocentric distance of 3.51 astronomical units. 40 kilograms per second is substantial. For context, a typical short-period comet might lose a few kilograms per second at that distance. So 3I Atlas is outgassing at a higher rate than many solar system comets. Now let's do the math. If 40 kilograms per second of water vapor is escaping, and assuming a typical ejection velocity of around 500 to 1,000 meters per second, the thrust generated is approximately 20 to 40 newtons. That sounds tiny, and it is. 40 newtons is about the weight of a gallon of milk on Earth. But in space, over weeks and months, even tiny forces accumulate. Jets are pointing. If the thrust is primarily radial, pointing away from the sun, then most of the outgassing is coming from the day side, which is expected.
If the thrust has a transverse component, pointing sideways relative to the Sun, then the jets are asymmetrically distributed, or the nucleus is rotating in a way that biases the net thrust direction. For 3I Atlas, preliminary models suggest the non-gravitational acceleration is consistent with the observed outgassing. The thrust matches the mass loss rate. The direction aligns with the jet morphology. So far, nothing anomalous. The object is behaving like a comet. But there's a complication. The composition matters. 3I Atlas has an unusually high carbon dioxide to water ratio, about 8:1 according to JWST data. Carbon dioxide sublimates at lower temperatures than water, which means it can drive outgassing even when the nucleus is far from the Sun. It also produces higher ejection velocities because CO2 molecules are lighter and move faster at a given temperature. If most of the outgassing is carbon dioxide rather than water, the thrust per kilogram of lost mass is higher, and the non-gravitational acceleration should be correspondingly larger. The models need to account for this. If you assume a pure water comet and the acceleration is stronger than predicted, that's a mismatch. But if you adjust the model for a carbon dioxide-dominated comet, the numbers line up. So the unusual composition doesn't create an anomaly in the dynamics. It just requires a more sophisticated model. There's also the question of sustainability. If 3I Atlas is losing 40 kilograms per second of material, how long can it keep that up? Let's estimate the total mass. If the nucleus is a sphere, 2 kilometers in diameter, with a density of 500 kilograms per cubic meter, typical for a porous comet, the total mass is about 2 billion kilograms. At 40 kilograms per second, the object loses 3.5 million kilograms per day. That's 0.175% of its total mass per day. Over 100 days, it would lose 17.5% of its mass. That's a lot. It's enough to cause significant changes in structure, possibly fragmentation, definitely a shrinking nucleus. But comets don't outgas continuously at the same rate. The mass loss rate peaks near perihelion when solar heating is strongest and drops off rapidly as the comet moves away from the Sun. So the 40 kilograms per second measured at 3.5 AU is not sustained for months. It's a snapshot at one moment in time. Farther from the Sun, the rate is lower. Closer to the Sun, it might be higher. Still, the implications are real. High mass loss rates mean rapid evolution. The nucleus might fragment. The jets might shift as new vents open and old ones close. The coma might brighten or fade, depending on how much material is being released. All of this is observable, and it's happening on timescales of days to weeks, not years. Now for the speculative angle. What if the non-gravitational acceleration doesn't match the outgassing? What if the thrust is stronger than the observed mass loss rate can explain, or pointed in a direction inconsistent with the jet morphology? That would be anomalous. It would suggest an additional force, something beyond natural outgassing. And while that could still be explained naturally, maybe internal pressure from subsurface vents or asymmetric sublimation, it opens the door to more exotic hypotheses. For example, if the object were venting stored gas from internal tanks rather than sublimating surface ice, the thrust could be decoupled from solar heating. You'd see acceleration at times or in directions that don't correlate with the Sun's position. That would be very strange for a natural comet. It would look more like a spacecraft venting propellant. But we're not there yet. The current data shows non-gravitational acceleration consistent with natural outgassing. The models work. The chemistry is unusual but not impossible. So the dynamics, as of now, support the comet hypothesis. Next, we tackle the chemical fingerprint. What the gases and dust of 3I Atlas tell us about its origin, and why some headlines are claiming it's emitting materials never seen in nature. Spectroscopy is the decoder ring of astronomy. You take light from an object, split it into its component wavelengths, and look for the dark or bright lines that tell you what atoms and molecules are present. Every element, every compound, has a unique spectral signature. Hydrogen emits light at 656 nanometers. Oxygen ionizes and glows at 507 nanometers. Water vapor absorbs specific infrared wavelengths. Carbon dioxide shows a strong band around 4.3 micrometers.
You measure the spectrum, match the lines to known molecules, and suddenly you know what the object is made of. 3I Atlas has been spectroscopically observed multiple times by multiple instruments, and the results are fascinating. JWST, the James Webb Space Telescope, used its NIR-SPEC instrument to measure the near-infrared spectrum of the comet's coma. The key finding was a carbon dioxide to water mixing ratio of approximately 8.0 plus or minus 1.0. That's extreme. Solar system comets typically have CO2 to H2O ratios ranging from 0.01 to maybe 0.5. A ratio of 8 means carbon dioxide dominates overwhelmingly. Water is the minority species. Why does that matter? Because composition reflects formation conditions. Comets form in protoplanetary disks, where the temperature and chemical environment determine what ices condense onto dust grains. In our solar system, water ice is abundant because oxygen is common and hydrogen is everywhere. Carbon dioxide forms too, but it's a secondary component. A comet with an 8:1 CO2 to water ratio suggests formation in a very different environment. Maybe a colder disk, where water remained in the gas phase while carbon dioxide froze out. Maybe a disk with different elemental abundances, less oxygen or more carbon. Or maybe the comet is just old, really old. A recent study explored the effects of galactic cosmic ray processing on interstellar comets. High-energy protons and nuclei slam into the ice over millions or billions of years, breaking chemical bonds, creating new molecules. One of the reactions converts carbon monoxide, which is common in comets, into carbon dioxide. If 3I Atlas has been drifting through interstellar space for 1 billion years, bombarded by cosmic rays the whole time, its surface layers could be heavily processed. Carbon monoxide converted to carbon dioxide. Water ice eroded or buried. The result would be an object that looks compositionally weird, not because it formed weird, but because it aged weird. That explanation is natural. It requires no exotic chemistry, no artificial materials, just time and radiation. And it fits the data. The high CO2 ratio is explained. The anomaly dissolves. But then there's the polarimetry. A separate study measured the polarization of light reflected from 3I Atlas and found an extreme negative polarization branch. Polarization measures how light waves are oriented, whether they oscillate in one direction or all directions equally. Natural surfaces scatter light in ways that produce characteristic polarization signatures. Dust particles, ice crystals, rocky surfaces, each has a distinctive pattern. 3I Atlas shows polarization unlike any other comet observed. The negative branch, the angle and degree at which polarization inverts, is more extreme than typical cometary dust. That suggests the surface or the coma particles have unusual optical properties. Maybe the particles are larger or more irregularly shaped than normal comet dust. Maybe the surface texture is different, more porous or more reflective. Maybe the composition includes materials with unusual refractive indices. Again, this is strange but not impossible to explain naturally. Comets are diverse. We've only observed a tiny fraction of the comets that exist, and an even tinier fraction of interstellar comets. 3I Atlas might just be sampling a region of parameter space we haven't seen before. Then there are the color claims. Headlines scream that 3I Atlas is turning green or emitting metal alloys never seen in nature. Let's unpack that. The green color is real but mundane. Many comets glow green because of diatomic carbon molecules, C2, in the coma. When solar ultraviolet radiation hits carbon-bearing molecules, it breaks them apart and creates C2, which emits green light at around 510 to 520 nanometers. It's a common feature. Comet Ison glowed green. Comet Lovejoy glowed green. If 3I Atlas shows green emission, it just means there's carbon in the coma, which is expected given the high CO2 content. But the metal alloy claim is different. An article in the New York Post reported that 3I Atlas was emitting a plume of nickel tetracarbonyl, a compound composed of nickel and carbon monoxide that doesn't form naturally in space under normal conditions. If true, that would be extraordinary. Nickel tetracarbonyl is an industrial chemical used in refining and metallurgy. Finding it in a comet's coma would suggest artificial processes or at least chemistry far outside the known range of natural cometary activity. The problem is the claim lacks peer-reviewed confirmation. No major observatory has published spectroscopic data showing nickel tetracarbonyl. The scientific community has not validated the detection. It's possible the claim is based on misinterpreted data, a noisy spectrum, or an artifact. Until it's independently confirmed, we have to treat it as speculative. Meanwhile, Meerkat, the radio telescope array in South Africa, detected radio emissions from 3I Atlas. Radio emissions from comets are common. They're usually caused by hydroxyl radicals, OH, which form when water vapor is broken down by solar ultraviolet radiation. OH emits a strong line at 18 centimeter wavelength. Meerkat's detection is consistent with OH. No alien signals, no anomalous frequencies, just normal cometary chemistry radiating in the expected way. So the spectroscopy paints a mixed picture. The carbon dioxide ratio is unusual but explainable. The polarimetry is extreme but potentially natural. The green color is normal. The radio emissions are normal. The metal alloy claim is unverified. We're left with an object that's chemically odd but not impossible. And to understand just how exotic, we need context. We need to compare 3I Atlas to its predecessors, the other interstellar visitors we've encountered. Before 3I Atlas, there were 2 confirmed interstellar objects that entered our solar system, passed through, and left. Each one surprised us. Each one challenged our assumptions, and each one taught us that the universe is stranger than our models predicted. The first was Oumuamua, detected in October 2017 by the Pan-STARRS telescope in Hawaii. Oumuamua was weird from the start. Its shape was highly elongated, possibly cigar-like or pancake-like depending on how you interpret the light curve. It showed no coma, no tail, no signs of outgassing. It just looked like a tumbling rock, dark and inert, speeding through the inner solar system at 26 kilometers per second. But then came the anomaly. Oumuamua's trajectory deviated slightly from a pure gravitational orbit. It accelerated away from the Sun in a way that couldn't be explained by the planet's gravity. The acceleration was small, about 1/1,000,000th of a g, but it was real and measurable. The natural explanation was outgassing. Even if we couldn't see a coma, maybe the object was releasing gas at rates too low to detect but high enough to produce thrust. Avi Loeb proposed an alternative. What if Oumuamua wasn't a comet but a light sail? A thin, reflective sheet pushed by solar radiation pressure. If it was artificial, built by another civilization, the acceleration would make sense. The lack of a coma would make sense. The unusual shape would make sense if it was designed rather than naturally formed. The idea was controversial. Most astronomers rejected it, but Loeb stood by it, and the debate continues. Then came 2I Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov. Borisov was the opposite of Oumuamua. It looked like a comet, it acted like a comet, it had a coma, it had a tail. Spectroscopy showed water vapor, carbon monoxide, normal cometary volatiles. The non-gravitational acceleration matched the outgassing. Borisov was reassuring. It told us that interstellar comets can be normal, familiar, understandable. But Borisov also had quirks. Its carbon monoxide to water ratio was higher than typical solar system comets, suggesting a colder formation environment. Its color was slightly redder, indicating different surface processing. And it fragmented as it approached perihelion, breaking into at least 2 pieces. So even the normal interstellar comet wasn't entirely normal. Now we have 3I Atlas. Where does it fit? Let's compare. Oumuamua had no coma and anomalous acceleration. Borisov had a coma and normal acceleration. 3I Atlas has a coma in professional observations but looks point-like in amateur frames. And it has acceleration consistent with outgassing, but also unusual chemistry and jet morphology. If Oumuamua was the weird outlier and Borisov was the normal case, 3I Atlas is somewhere in between. It's more active than Oumuamua, showing clear signs of outgassing and jet activity, but it's less straightforward than Borisov, with compositional anomalies, unusual polarimetry, and the whole missing coma mystery in short exposure images. The pattern that emerges is diversity. Interstellar objects are not all the same. They come from different star systems, different formation environments, different histories. Some are icy, some are rocky, some are ancient and heavily processed, some are young and pristine. We can't generalize from 3 data points, but the 3 we have suggest a wide range of possibilities. What we've learned from the earlier objects matters. Rapid follow-up is critical. Oumuamua was discovered late, already on its way out, and we missed the chance to study it in detail. Borisov was caught earlier, and we got months of high-quality data. 3I Atlas was detected far out, giving us time to prepare, to schedule observations, to coordinate international campaigns. That preparation is paying off. We're getting the data we need. Wideband spectral coverage helps. Observing invisible, ultraviolet, infrared, and radio wavelengths reveals different aspects of the object's chemistry and activity. Multi-wavelength imaging shows how the coma and jets look in different filters, highlighting specific molecules and particle sizes. And patience matters. Jumping to conclusions based on preliminary data is tempting but wrong. The scientific process requires confirmation, replication, peer review. The headlines that scream alien spacecraft or green death comet are entertaining but premature. The truth emerges slowly, one observation at a time. Now we shift from the object itself to the ecosystem around it, how data is shared, how leaks and social media shape the story, how the gap between scientific rigor and public curiosity creates tension. Science used to move at the speed of journals. You'd make an observation, write a paper, submit it for peer review, wait months for feedback, revise, resubmit, and finally publish. By the time the public heard about your discovery, it had been vetted, analyzed, contextualized. That system had flaws. It was slow and exclusive, but it ensured quality control. Social media destroyed that timeline. Now, an amateur astrophotographer in California captures an image of 3I Atlas, posts it to YouTube or Twitter within hours, and suddenly thousands of people are discussing it, speculating about it, forming opinions about it, all before any professional scientist has had a chance to analyze the data. The clip from Chuck's astrophotography went viral. It spread through forums, Discord servers, Reddit threads. People started calling it the alien comet, the green visitor, the mystery object. And scientists, the professionals with PhDs and access to big telescopes, found themselves playing catch-up, trying to explain what was real and what was hype. That tension is healthy but exhausting. Amateurs are contributing real value. Thousands of backyard astrophotographers around the world are pointing their telescopes at 3I Atlas, capturing images, sharing data. Some of them have excellent equipment, precision mounts, cooled CCD cameras, software that rivals professional pipelines. Their observations are valuable. They provide temporal coverage that single professional telescopes can't match. They catch transient events, sudden brightening, jet outbursts, changes that happen on timescales of hours. But amateurs also lack the training to interpret their data correctly. They don't always calibrate properly, they don't always account for atmospheric effects or instrumental artifacts. They see patterns that aren't there, or miss patterns that are. And when their images look different from professional images, they jump to conclusions. The missing coma becomes proof of alien technology. The compact appearance becomes evidence of a spacecraft. The speculation spirals. Social media amplifies that spiral. Algorithms reward engagement, and sensational claims get more engagement than careful analysis. A tweet saying 3I Atlas might be a comet gets a few likes. A tweet saying 3I Atlas is definitely an alien probe gets thousands. The incentive structure pushes toward hype, not accuracy. Scientists feel the pressure. When the public is buzzing about your research object, when journalists are calling for quotes, when social media is demanding answers, you're forced to respond faster than you're comfortable with. You haven't finished your analysis. You haven't published your paper. But if you stay silent, the speculation fills the vacuum. So you release preliminary statements, cautious and hedged, and those statements get misinterpreted or ignored because they're not dramatic enough. December 19th is coming, and when it arrives, we'll know. Either this is an unusual comet behaving strangely under extreme conditions, or we're looking at something that forces us to rethink what's possible. Subscribe if you want to find out what happens next.